Roksolana. I work as engineering manager at Captify. Captify builds a product in advertising sphere. Also, I'm one of the leads of Women Who Code Kyiv community and Women in Machine Learning and Data Science. And I often speak at conferences and various meetups. So, as I said, the company where I work, Captify, builds products in AdTech. So, what is AdTech, kind of in comparison to advertising in general? So, they call AdTech as a sphere which is kind of advertising on steroids, meaning that we have a possibility to actually run advertising campaigns for specific users. So, we try to deliver the right content to the right time to the right consumer. So in the past, you could remember that often you could see some ads on TV, and in a lot of cases, they were not relevant, just some kind of abstract ads, while AdTech is more around trying to target specific users and kind of push some products that the brands want to sell and find the right users for those products. And basically, consumers win on that side as well because they get to find out more about the thing that they're actually interested in. Yeah, okay. So what Captify specifically does in AdTech, we categorize, collect billions of real-time search events from users. So what the users input as their Google search can be kind of gathered, and then based on this data, we are able to figure out what kind of users we have and create so-called segments or audiences out of these users. So for example, if someone is looking for some toys for their pets, they end up in a segment or category called pet owners. And in the future, when the brands are trying to sell something for people that own pets, they will be actually looking for the users in that category. So in terms of tech stack that we have, the product is quite big. There are a lot of teams. The team that I work on is basically works mostly with data ingestion and a bit of reporting. So the tech stack that we have is a bunch of data sources, usually the files that we get on Google Cloud, Amazon S3, and a little bit on HDFS. We have mostly Spark jobs, both batch and streaming jobs, Kafka and Flink as well for streaming, and we dump the data for Cloudera Impala, but we are kind of migrating now to Databricks, where the data is going to be available for internal users mostly. So as I mentioned that, let's imagine the case that you already build the pipelines, and my company has been building those for around 9 or 10 years, and they've been evolving over those years. And you have your pipelines already running in production, so what happens next? And there are multiple types of issues that can happen with the pipelines. First of all, I think the case that happens the most often is low performance. I think this is the biggest issue in big data pipelines because we can't always account for the amount of data that we are going to ingest. Sometimes the data load can change. With streaming data, it's even more different. So having low performance with our jobs is often the case, and we often need to optimize, especially when the time passes and there are some changes downstream. Another issue is unexpected results of the algorithm. So it often as well connected to the data source because sometimes we get just more data and our algorithm didn't just account for this amount of data. Or there are some changes in the data formats, and again, our algorithm didn't work with that. So sometimes something that we built in the beginning and we roll it out in production may evolve over time. And also data source errors. Those don't happen really enough in my case, but they do happen sometimes. And we have a lot of data providers external, and that's why they push the data in very different formats. And there can be issues like with missing data, with some changes in the data. And that's why I think those issues are actually easiest to debug, just to check what happens at the data source. But at the same time, they happen from time to time. And human errors, like running some query which you didn't want to run, pushing some data you didn't want to push. So there is always a chance that someone just does something, and it also kind of ruins the pipeline in production. So story number one is called unlucky query. So we all have, I think, those types of queries which we wished we didn't run in production, especially. And it happens sometimes that either like the rights or authorization is messed up in some way, that someone just gets more access to production, or someone who actually like has access to production just uses it in their own way. And therefore, sometimes we have cases where some query runs and something wrong happens basically with that query. So this is the case. We have a pipeline for reporting purposes. So we have the users which just look into the data in Impala. For them, it looks like a simple table. They run SQL queries. They just look into the data, run their selects, aggregations, everything they need. Behind the scenes, we have just a Spark job that gets the data from HDFS and pushes this data to Impala via a Parquet format. So Impala is not a database, it's a query engine which is built on top of HDFS. Therefore, behind the scenes, we actually just push the files from one HDFS to another in a bit different format, plus add kind of the metadata layer where Impala is going to understand that it's actually a table which has these types of columns, these names, and so on and so on. So what happens here is that suddenly someone runs the query which drops 13 months of data called user profiles. User profiles is demographical data which has some info about kind of age, gender, and all of that stuff. And this is not the most critical pipeline, luckily. And this is a pipeline, the type of data that we receive from another team. And suddenly we don't have this data for like 13 months in Impala, which is not, doesn't make users happy, definitely, when they don't have this amount of data. And this is actually quite a lot of data to reload. So the problem that we have, as I mentioned, that HDFS is kind of behind the scenes here. We have the source from another team, HDFS, Parquet files partitioned by hours, so everything is fine with our data source. But it's not okay at the end of the pipeline for the users which use Impala. So we also need to have these Parquet files on HDFS and kind of display them via Impala for our users. So 13 months is quite a lot of data, as I mentioned. It's partitioned by hour, so we can reload hour by hour. But anyway, it's quite a lot of data. And basically, this is kind of query you would want to revert. So the loading mechanism that we have just installed in our jobs is managing this period to load concept. So basically, we have like this day, current time, and when we are loading the data, we take some smaller period, like 5 days up to a month, and we are kind of reloading the data back in time. So if I would run the job, for example, today, we are going to load the last 5 days from today back in time. So in this case, as you can see, we're just kind of using those dates to figure out the period that we're going to reload. And what we actually need in this case is set it up to 13 months just to reload 13 months. So the reason just setting up to 13 months is not going to work is because, as I mentioned, a lot of data in the job, even with bigger resources, is not going to handle that. So what we did, we tried to reload first by like 2 months or 3 months, which didn't work as well in terms of resources. So we essentially just switched to 1 month, and once month by month, we were able to reload that. But it took quite a lot of time, actually, around 1 week and a half, and because the data load is quite huge. But luckily, we reloaded quite quickly the last months. And usually for reporting, like the last months or the last quarter are the most critical. That's why for them, like the whole 13 months reload was not as critical. And they were able to wait for the whole 13 months to appear in Impala. So that's how we resolved that kind of unlucky query issue. Another story is around missing data. And this is something that happens really often in various pipelines, whether at data source or somewhere downstream. So at some point, we just see that we don't have data anymore. And this is kind of the point when we need to wear our debugging hat and figure out on which step of the pipeline it happened. So we have this pipeline with 2 main jobs. And we have the data that we get from data partner let's call the data partner X for kind of NDA reasons. And the data partner drops the data on Google Cloud. We just get this data via extractor job, do some reprocessing, partition the data, drop some columns, and then push it to Amazon S3. And then a much larger job called data cost attribution fetches this data and runs a lot of steps that it needs to run. So we're going to dive a bit deeper into this job a bit later. But basically, the main thing that this job does is just get into data, figuring out what kind of segments used in various campaigns, and calculating data costs on top of that. So if you worked already with Spark, you know that any kind of aggregating of data costs and some formulas calculation on a huge amount of data can be quite costly in terms of pipeline. That's why I say that this is quite a heavy job. So what we have in terms of missing data is that we don't have the data on HDFS, which is kind of the final destination for the whole pipeline. And we need to figure out what actually happened with that data and on which step of the pipeline it disappeared. So during some debugging phase, I looked into the data and figured out that actually the data provider didn't mention that they renamed the columns a week ago, because this is like the point when we started to miss the data. And they just changed the name of their data provider kind of officially to a bit different one a while ago, but they didn't touch the data for this time. And then suddenly they decided to actually just rename the columns as well. So we used to have kind of X advertiser ID, for example, and now we have 2 X's. So what happens is that our pipeline is kind of heavily depends on the names of the columns, because one of the steps in that data cost attribution pipeline is choosing the columns that we are going to use. And therefore, we are definitely using the names of the columns. And what just happens is that we can no longer find those columns. So the job just runs without any data. Nothing happens. We don't have any result in the end, in the destination. So what we need to do basically is just rename the old columns, which kind of sounds simple, and reload the whole data for the week, because that's been like the whole week since we missed this data. It's not actually that easy with the renaming, because let's remember the fact that at some point they changed the names of the columns, but in the past we also had kind of different names. So we have 2 versions of the data now. The one kind of a week ago with some X and name of the column, and the one right now which is 2 X's. So we kind of need to tread lightly here and figure out how to be able to run the job based on these 2 types of data, which is not like too complicated. The code here is in Scala, because most of the jobs are in Scala for Spark in my team. So we just put some regex, kind of figure out that some old columns still stay the same. We choose those columns as well, but in the case if our new columns suddenly, if our columns got changed, we are going to switch to a bit different version and kind of rename all the columns to this new version. So in this case, this step happens, and after that we can just choose all the columns with a newer name, and we don't have to worry at the point when something else happens. We just kind of need to be cautious as well in case of any other changes in the future, because if something happens and we have like a third naming, it's gonna be not so much fun. But either way, in this case, we just rename all the columns and work with the newer ones, and everyone's happy. So in the end, we kind of have this bunch of columns with 2 axes. We run all of our pipelines based on top of that, and it kind of works out, and everyone's happy, and we no longer have missing data. Also, the reload with week of data was not kind of that heavy, because the data source that we use for data cost attribution is not kind of heavy in terms of the amount of data we receive in comparison to other data partners. So it worked out well. We were able to rename the columns, and that's kind of the way it has been running in production with those changes. So another story that I'm going to share is called divide and conquer. So there are cases sometimes, which I mentioned around bad performance of the jobs, when we, instead of solving the problem for kind of the whole data load and a bunch of data that we have, we can solve the same problem for kind of smaller data set, and that's why kind of divide and conquer, and then just extrapolate it to the bigger one, which is kind of the whole data set that we have. So what happened in our case, we have Spark job, which reads the data from Amazon S3, with Parquet files partitioned by processing times, and drop them to another bucket with created partitioning. So it's not kind of complicated, but there is quite a lot of filtering there and aggregations in the job itself, and it deals with the so-called segment feed. As I mentioned, the segments of the users and audiences, and we have really a lot of historical data about that. And that's why we have huge amount of data, which we call state. So we have some current state of the audiences, and we upload this data from one S3 bucket to another. So the problem here is that the job starts to fail, and it actually consumes really a lot of resources to restart, to reload more and more data, and our state starts to grow. So initially, the reason is that we have more and more data over time. And the job with current resources, even with kind of increasing of resources, doesn't really work well. It processes the data very slowly. Specifically, for example, it used to process the data up to 2-3 hours, then it gets to 6-8 hours, and it's a very long time for the users to wait. And it's also part of the bigger pipeline, only one of the kind of multiple steps between different teams. And that's why it causes a lot of trouble for other teams to get this data and continue working with that. And as a result, because we work with kind of the whole state per each partition, as I mentioned, for processing time, it's still quite big, even though we work with time and not with date. We have really large Parquet files, which are not convenient to work with in the future with other jobs that we use. And that's why we have kind of a lot of issues here: bad processing, failing job, large files. So in this case, actually dividing it into smaller chunks should work much better. So what we did is change the partitioning, and I think it's kind of a common mechanism in Spark. If you suddenly have a lot of workload on your Spark driver and you have a lot of data, the best approach is to actually just create more partitions, because your partitions can be too big. So as I mentioned, why we have large Parquet files, because in one process time, the partition is quite kind of big in itself, and the executors are not able to process that. And that's why we also, kind of the nature of the data doesn't allow to use any other columns for partitioning, because sometimes we are looking for some IDs, for some time, anything like that, but we don't have any kind of more data to use that. And we create so-called seed partitioning column, which is basically just generation of hash, in our case with 2 columns, full URL and domain that we have in the source data. So we create the hash, we a bit experiment with kind of the better ratio in terms of the hash to use, because you can just throw a random value there. And then we have smaller partitions, and we are able to kind of process them better. Then we write this new partition state to S3 bucket, and all the next jobs downstream are able to process smaller chunks of data, and they don't have to deal with this like large state. They only deal with the smaller ones. So this is how it looks like actually. In the beginning, we had these partitions by processing time and some random name of the Parquet files. In the end, we have created partition, and in each of those, we have so-called bucket partition from 0 to 9. 9 is not a kind of random number. It was just experimented that it works better with the current workload, but obviously it can kind of increase and decrease as well. And we have a bunch of Parquet files in each of those buckets. So in the end, when we have downstream jobs, they're just going to work with some specific bucket, for example, or process the data bucket by bucket, and it's much easier for a Spark job to work with this data load instead of kind of the whole created partition, which is too large. So it's a common solution for a lot of cases when we have large data in terms of both data source and how we produce the data, so kind of dividing it into smaller chunks and smaller partitions. And it actually solved this issue for quite some time, and we haven't been like experiencing any performance problems with that pipeline specifically, but also it's a good approach in general to tune it a bit in the future if necessary, and there is no need to just throw kind of more resources to Spark jobs. So another story that I'm going to share is called Catch the Evolution Train. So basically what happens sometimes, if you have some person in your company or your team which is kind of very visionary one, whether an architect or someone who just has kind of enough power in a way to change some data layout, some tech stack that you use. And this person kind of has this vision and they are trying to push to just create, kind of make it real as fast as possible. And that what happened to us. We had for a while a vision on how we want to change the data layout because, for example, as I mentioned, Impala didn't work really well for us anymore because it's better for some ad hoc queries, while the data analysts, as the users of Impala, used mostly for larger queries. So it didn't really work well in terms of performance. It wasn't very convenient for developers. And over time, we decided to switch to data mesh and basically the Delta Lake organization of the data. So what we have is very different types of jobs, which in this case would be like on different layers of the organization. What we want to achieve is having some data sources that we push and kind of three main layers of this data, which is ingestion layer. It's kind of mostly raw data, maybe a bit of pre-processing there. Another layer is silver, which is a bit of processing and filtering. And the last one is aggregated. So, for example, the jobs that I already mentioned with just ingestion and extraction would be on ingestion or bronze layer because they deal with raw data and a bit of changes of the columns, but they don't deal with any additional processing. While the job called data cost attribution, for example, would be either on silver or gold layer, depending on the transformations that we have for a specific data provider. So this is what we want to achieve, but as I mentioned, in reality, different teams have different pipelines on different layers. We had the idea that, for example, my team mostly on the ingestion side, and that's why all of the data that we push should be on bronze layer, which is not exactly how it works, because sometimes we have jobs that expose the data on both silver and gold layer as well. And as I mentioned, that we have some steps missing for some of the jobs because we just kind of get the data, do some calculation and drop it somewhere. So the users are not able to see kind of in the middle of it, or sometimes they don't have access to raw data, and this is something that they would be kind of interested to see as well. So what happened basically that since we are working on that migration and there was this like great idea that we need to complete it this quarter as fast as possible because it's been a while since we wanted to build this vision. And so another team just comes to my team and say that there's been some missing columns from the source, and they would want to see kind of more columns of that because the users complained about that. So we have now dependency with another team. We need to expose more columns for them. And it actually very critical because it just stops for them to migrate from Impala to Databricks. And it's kind of a critical thing that they want to do during the quarter. So it's more like a business dependency in a way. And we have unhappy users in the end, which are the analytics team, which don't see the data that they want to see. And they want to build some kind of reporting and pipelines and understand how the raw data that we get from data providers looks like. So the pipeline that I already mentioned, called data cost attribution, look like this. We have multiple steps. Log level data is the data that we get from data providers with so-called user events. User events is how the user reacts to ads on the browser or in any window. So basically, the types of reactions are impressions, clicks, and conversions. So the user can see the ad, click on it, make a conversion, basically, watch the video, for example, as well. And then we receive these events as a log level. So basically, by kind of millisecond level, there's a lot of source data because of that. And we have different steps like ingesting the data, cleaning it up a bit, maybe renaming some columns. Then we have a mapper step where we just remap the columns by renaming them and choosing only the ones we're interested in. So we had in the past this issue with renaming of the columns because of this step specifically, because we choose kind of specific columns only. We have a transformation step, which runs a bit of filtering, some joining, aggregations, and it's actually the most kind of critical step of the pipeline, which drags most of the performance there, because kind of the main problem that data cost attribution solve is figuring out whether the users that we targeted in the beginning are actually the same ones that watched the ad. So what happens there is joined between our audiences or segment feed and the information that we receive in those log level data, trying to understand kind of is it the same users or not. And then we run data cost calculation and drop it somewhere. So what we want to achieve here is that we have this multiple steps of the pipeline. You're already familiar with a bunch of those. We have Google Cloud as a source, this data extractor job, which drops the data to Amazon S3. We have attribution job, and in the end, the way that the users see the data is via Impala. So we have so-called Impala loader job. So you kind of basically already familiar with the previous stories with how it works step by step, but this is just a general view how it looks like. So we want to either see those missing columns in the step Amazon S3, where we have the results from data extraction. So it's usually kind of raw data kind of level, bronze one. Or we want to see it as a final result of data cost attribution on HDFS, which is gold level. So talking about kind of waiting out these opportunities and trying to figure out what's better, we kind of decided that actually seeing it in the raw data is better in terms of both performance and just logically, because the users want to see as much data as possible from the raw source. And therefore, if we expose it on that level, we are kind of able to make the users happy and at the same time be closer to the final vision that we have around the data mesh. Or if we would work with data cost attribution pipeline and try to expose the columns there, we would have to stumble a bit on some possibly performance issues, because adding new columns to already kind of heavy pipeline with which leverages terabytes of data every week is not like the best idea. Plus, we already have some kind of schema as a final result for the whole attribution pipeline, which we don't want to kind of ruin with some additional columns and just break this unification. So what we did is, as I mentioned, decided to change the raw data job, and we added some columns. And indeed, when we just look into kind of comparison to how it was in the past and how it looks like now, we have 82 columns instead of 26, which is quite a big difference, more than kind of 2 times. And that's why it's going to be a bigger load if you would add it to data cost attribution pipeline. And this is like a better approach here because, again, we are exposing the data earlier and the users can see the raw data without any additional aggregations, and then they can just look into the data that they are interested in an aggregated manner. So as I mentioned, this is a solution. We had this data extractor job, which is Apache Spark here. So we dropped this data on Amazon S3, and we added one more step to pipeline, which we renamed the columns, changed the format a little bit, and dropped this data to Databricks because we are migrating to Databricks, and the users can just see the data that they are interested in a raw format in Databricks. So the final step of solution was just writing the data in a partition manner by event date and event hour to some destination path. So we kind of should be happy we came up with this great solution, but not so fast. So the reason this solution didn't really work is actually the nature of the source data. So at some point, while we were testing, we just noticed that as a final result, for some reason, we get the files only of one type, while in the source, we have 3 types of files: clicks, views, and activities. So what happened here is that the pipeline just takes the most recent data for specific event date, because we have partitioning by event date. It doesn't check that actually there are more files of different type with the same event date. We just already see the partition being written down with Spark, and we don't need to kind of come back and see if there is more data in that partition. This is the way Spark works. And that's why we need to somehow do something about it so that our Spark job would be able to see that there are different types of files, that we need to all write them down in different partitions. And what we were thinking about is that actually if we would drop kind of clicks and views and activities in one Parquet file by each event date might not be like the best idea, especially if they have a bit different schema. And also kind of joining 3 files into one could be a heavy job as well and not so fun. And the users actually said that they analyze the data separately by different types of events: clicks, views, and activities. So they just view mostly impressions. This is like the way data source looks like in terms of ratio of different types of events. They also look into clicks and conversions, but those are not the main ones because we usually have more impressions and we have more data about impressions from each of the advertising campaign. So that's why we thought that maybe we could deliver the data separately to them. And actually, we already have another job which does just that. And instead of just building one huge Parquet files, which contains both impressions, clicks, and conversions, we can deliver them separately. So this is what we did. We just dropped all the files of clicks, nature, into one folder with partitioning by event date and event hour. Same for impressions and same for conversions. You can see here differences in naming a little bit for this specific data provider. And then we expose this data via Databricks, and kind of the users are happy and they can see the raw data. So conclusions out of all of those stories. First of all, as you noticed that backups were actually very helpful, like in the case where we had issues with the kind of drop in the data. If we wouldn't have a lot of data in the source, it would be a much bigger problem if we would have to somehow find this data somewhere or kind of reprocess the whole mechanism of user profiles generation and then kind of reload it separately. So just having a backup or building pipelines in this manner where you have multiple steps and you are able to write some cache or additional data somewhere is much better. And also flexible loading mechanism is helpful too because you are able to kind of tune in your pipelines. So in that case, we didn't need to kind of change really a lot of steps or anything basically in the pipeline for reloading the data. We just changed configuration. So we were kind of already prepared for some cases when we need to load more data than usually. Then data source checks could be very helpful. It's either via some alerting techniques or maybe something built in into the pipeline. What we usually have is some alerts via Prometheus where we just check if we actually have data in the data source. And if we have some kind of warning that, for example, yes, we don't have this data anymore, we need to do something about it, we can reach out to the data provider directly and ask them what happened. And of course, kind of debug because of before that in case of some columns renaming or anything like that. And there can be some additional data source checks. We were thinking about doing something around schema changes. So in the cases of renaming, we would be kind of prepared for that. Another conclusion is that data evolution is hard because it's kind of messy. What we were trying to do is removing Impala and migrating to Databricks. And the case that I mentioned is kind of only one in multiple because we have maybe like 200 pipelines in different teams kind of spread out between them with different layers of the data. And that's why the team that works mostly on migration is kind of suffering a little bit with migrating all of those pipelines and even worse, historical data load and not only recent data and all of the schema changes. So it's quite hard, and that's why still a lot of teams should be involved with supporting any kind of data evolution and supporting basically the vision for that too. So thank you for attention. Here's my contact info. Twitter, GitHub, LinkedIn, and SpeakerDeck. I'll drop the slides on SpeakerDeck so you'll be able to see them. And also the QR code is for donations for Ukraine because I'm based in Kyiv, Ukraine, so be happy for any kind of support on that side. So thank you, and I'll be happy to hear any questions.
Hi. When you talk about data evolution is hard, how could you handle this in a general idea? I am talking about it's hard, as could you say, but do you have a methodology, a general methodology to that?
Yeah, okay, thanks for a question. So I wouldn't say that there is a methodology because I think that multiple companies approach it in different way. Probably I would say that it should be always more structured. In our case, why we kind of hurry is that because it's been maybe like 2 years since someone came up with this idea and it's been too long, and everyone's kind of trying to finally do that. But what helped to actually make it better in a way is that there is still a plan on how to do that, on how to migrate teams, and it wouldn't be much more painful if like all the teams decide to just do it in 1 quarter. That would be impossible. So it's not like it just happened once, and that's why I think that the best approach is to try to build a plan with gradual migration, especially if there is like a lot of legacy pipelines. First figure out like how the user is going to look into this data, work with them, and ask their feedback a lot, and then try to kind of build these different layers of the data, reload it historically as well, and just support it basically. Thanks for your question. Okay, thanks a lot for your attention, and don't forget to rate the talk in the Codemotion app, and have a great conference.